All right, class, let's get settled. Welcome. Think of this as our big final exam study session. We're going to pull back the curtain on machine learning. But listen, we're not just here to memorize a bunch of terms. Nah, we're learning how to be architects, how to actually design and build what you might call digital minds, right from the ground up. Okay, so here's our game plan for today. We'll start with the biggest choice you have to make right at the beginning. Then we'll cover the basic tools of the trade, see what happens when we combine them, and then we'll venture out into the wild, learning without a map. And finally, we'll get to the really cool stuff, the modern power tools on the neural frontier.
So every single project starts with one huge decision. This is probably the first question you'll get on an exam, and for sure the first one you'll face in the real world. Are we giving our model a teacher, with an answer key to study from? Or are we just throwing it into a library with no catalog and telling it to find the patterns all by itself?
This really breaks it down perfectly. On the left, you've got supervised learning. It's all about making predictions. You have the inputs and you have the correct outputs. That's your answer key. The entire goal is to learn the secret recipe that turns one into the other. Then on the right, you have unsupervised learning, which is all about discovery. There is no answer key. The goal is to find the structure that's already there, the hidden story buried inside the data itself.
Okay, time to open up our toolkit. Every great architect starts with the basics, right? A ruler, a measuring tape. In our world, that's linear and logistic regression. Seriously, don't underestimate them. They're simple, they're elegant, and they are surprisingly powerful. Pretty much everything else is built on top of these ideas.
So, rule number one is knowing which tool to grab for which job. If an exam question asks you to predict a number, a quantity that can be anything on a scale, like a price or a weight or a temperature, your brain should immediately go, aha, linear regression.
And the intuition is it's just so simple. Imagine all your data points are just scattered on a graph. Linear regression is basically just taking a ruler and trying to find the one single straight line that cuts through the data in the best possible way with the least amount of error. It's always looking for the simplest relationship possible. The catch? Well, its biggest limitation is that it assumes the relationship is a straight line.
Which, of course, leads us to the next obvious problem. The world isn't always about how much, right? A lot of the time it's about which one. Is this email spam or not spam? Is this customer going to leave? Yes or no? Our straight ruler, well, it just can't answer that kind of question.
For that, we need a different tool. We need logistic regression. Its whole reason for being is classification. Instead of predicting a number that could go up to infinity, it's designed to predict the probability that something belongs to a certain group. And this is the cornerstone of so many applications you see every day, from medical diagnoses to figuring out if a credit card swipe is fraudulent.
So how does it pull that off? Well, it takes a regular linear prediction and funnels it through this special function that creates this very distinct S-shaped curve you see here. It's called a sigmoid. And what's cool is, no matter what numbers you throw at it, the output is always squeezed between 0 and 1. And that makes it absolutely perfect for representing a probability, like, say, a 70% chance of rain.
Okay, so we've got our basic tools down, but what happens when a problem is just too messy, too complex for one simple model? Well, what do we do in real life? We ask a bunch of experts, right? We get a second, third, fourth opinion. And that is the whole idea behind what we call ensemble methods. We combine lots of simple, kind of weak models to create one that's incredibly powerful. And the basic building block for a lot of these ensembles is the decision tree. This is probably one of the most intuitive models out there because it literally thinks the way a person does. It's just a big flowchart of yes or no questions that guide you to a final decision. It's transparent, it's easy to explain, and it can be really, really effective. The key to a good tree is that it doesn't just ask random questions. The algorithm uses math to figure out which question will split the data most cleanly, getting rid of the most uncertainty at every single step. It is exactly like your strategy in the game 20 questions. You always ask the big, important questions first.
But here's the problem, the big weakness. A single decision tree can be, kind of twitchy. It's very sensitive. You change just a little bit of your data and you might get a completely different tree. It has this tendency to just memorize the training data, which we call overfitting. So if one tree is unstable, what's the solution?
Simple. We build a forest, a random forest. Now, the genius behind this is that we build hundreds, sometimes thousands of different trees. But the trick is, each tree only gets to see a random little piece of the data. This makes sure all the trees are different, they all have slightly different perspectives. Then, to make a prediction, we just let them all vote. The majority wins. And this brings us to a super important trade-off. It's a classic dilemma. With the random forest, you get this massive boost in accuracy, and it's incredibly robust. That's the huge pro. But, and it's a big but, you lose that beautiful simplicity of a single tree. The model becomes more of a black box. You can't just point to a simple flowchart anymore to explain why it made a certain decision. Power versus interpretability.
Okay, let's totally switch gears and jump back to that other world of learning. What happens when you have zero labels, no answer key? This is unsupervised learning. And it's less like being a student and more like being an explorer, searching for hidden continents of structure in just this vast ocean of raw data. This is where the machine really does the discovering for us.
And the classic tool for this kind of exploration is k-means clustering. The goal here is pretty simple. You tell the algorithm how many groups, or clusters, you think are in your data. That's the K. And it automatically sorts every single data point into those groups based on how similar they are to each other.
A great way to think about it is like this. The algorithm just randomly drops K center points into your data. Then it assigns each data point, each book, to whichever center point is closest. Then it recalculates the center of each new pile and does it all over again, and again until the groups stop changing. It's an amazing method for things like customer segmentation or organizing millions of documents.
So, we've covered the classical toolkit. But now, we're going to the frontier. It's time to pick up the power tools, the models that are inspired by the most complex machine we know of, the human brain. Welcome to the world of neural networks.
And believe it or not, this entire incredibly complex world starts with one single simple unit, the perceptron. Just think of it as one digital neuron. It gets a bunch of input signals, it decides how important each one is, and if the total signal is strong enough, it fires and passes on a simple yes-no decision. That's it.
Now, if you start stacking these neurons in clever ways, you get specialized tools. Convolutional neural networks, or CNNs. These are the vision experts. See, they don't look at a whole image at once. Instead, they use these little filters to scan across the image, looking for tiny patterns. First, it's just simple edges and corners, then maybe eyes and noses, and finally, whole faces.
But what about data that happens over time, like language or a piece of music? For that, you need memory. Recurrent neural networks, or RNNs, have this really cool feedback loop. It allows the network to remember what it just saw a second ago, which gives it context to understand, say, the very next word in a sentence. But even RNNs were a bit slow. They had to process things one word at a time. Then came the revolution, the breakthrough that powers models like ChatGPT, transformers. And their core idea is just so cool. It's a concept called attention. Instead of reading a sentence one word after another, a transformer looks at all the words at the exact same time and calculates how important each word is to every other word. This unlocks this deep, almost human-like understanding of concept. It was a total game changer.
And that brings our study session to a close. We've gone all the way from the simplest line drawing tools to these incredibly advanced architectures that are literally changing the world as we speak. You now have the blueprints for the Architect's Toolkit. But remember, no single tool is perfect for every job. The real skill of the architect is knowing which tool to pick for the job at hand. Now, go build something incredible. Class dismissed.
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.